Hi everyone, and welcome to this tutorial by For Oxygen Not Included, which is an introduction to automation. This is a powerful tool to set up more complex systems that can manage themselves. I've decided to split this topic into two tutorial bites, and this first one will cover the basics and practical applications. In reality, most automation that you need to run even an advanced base is quite simple, so this should cover almost all the useful automation in the game. Chapters are available if you want to jump to relevant sections. So let's start with the basics and automation wires. These wires are made of refined metal and carry signals so we can control things. There are two possible states these can have, green and red. You can also think of these as on and off, as most buildings that receive these signals use it to turn on and off. The other way to think of these are red as 0 and green as 1, and this is binary, meaning the two states. I wanted to point out that this automation is based on real-world digital electronics. Don't let that put you off, but instead I think it's cool that we can learn this through the game. Whatever device you're watching this on is using digital electronics and binary, so this might give you a little insight into how they work fundamentally. So now we have wires that carry signals. We of course need buildings that output signals and those that receive them. Buildings that send automation signals are generally sensors, and that means the signal they send depends on some environmental condition they are sensing. I'm showing some common sensors here, and you can see in the automation overlay that they have an automation output port. These will send out a green signal if their condition is met, or will otherwise send red. Hovering over this port will tell you what the condition is. Many of these sensors are also configurable, so you can choose the condition more specifically. The benefit is that sensors will automatically react to a change in conditions, and then we can react to that change. And to do that, we need buildings that receive automation inputs. Generally, these simply turn on with a green signal and off with a red one. Again, the description is found on the automation input port in the automation overlay. There are a few exceptions to the on-off rule, and a common one is mechanized airlocks that open and close instead. As a quick note, be aware that some buildings have both an automation output and input. Remember to check the automation overlay to see which port is which and what they do. So with these two types, sensors and receivers, we can now make the simplest of automation setups by directly connecting the two with a wire. Now the sensor controls the machine, so we have an automated system. I should also say that although this is a simple setup, it's probably the most powerful and most common type in the game. Most of the automation in even an advanced base will simply be sensor, wire, machine. So if you've got this concept, then you can build most of all the automation you'll need. I'll cover some examples next, but before that, I want to introduce an idea that I'm calling a worded logic statement. Many people may find it difficult to design an automation system from the idea they have of how it should work, so this is a useful concept to take an idea and make it in-game. These worded logic statements are in the form if, then. So if some condition changes, then we will do something about it. If you're struggling to design a system, then it may help to write this out using words first. I've got two example ideas to clarify this. In the first one, let's say that we want to only light up an area when dupes are nearby. So the worded logic statement would be if there is a dupe nearby, then turn on the light. Detecting dupes is done with the motion sensor, and the light is a straightforward input. So building this in-game means a motion sensor with a wire to the ceiling lamp. In the second example, we want to heat up an area if it's too cold. So the worded logic statement is if the temperature is below 5 degrees, then turn on the tepodizer. And here the temperature is detected with a thermosensor, and the tepodizer input is straightforward again. Hopefully you've got the idea, so we will run the wire from the thermosensor to the tepodizer and set the thermosensor setting to below 5 degrees. I'm now going to cover three of the most common examples that I use in my bases, and all of these use a single wire. The first is for gas and liquid pumps, using an atmosensor and hydrosensor respectively. These are used to stop the pumps completely clearing an area and to avoid pumping small packets which consumes the same amount of power. So the setting for the sensor is set to green if there is enough gas or liquid to pump. Common settings are 1,500 grams for gases and 100 kilograms for liquids. Next is the smart battery, and this is usually the first automation that I build in any base as it's really important. The smart battery sends green when the low value is reached and it needs charging, to then turn on the generators. Once the battery fills, reaching the high value, it will turn red. This saves fuel and reduces the heat and waste products made. I covered this in more depth in the tutorial bite for power generation. The last single wire example is in a cooling loop. Again, I explained cooling in full in its own tutorial bite, but this is a common automation example. The liquid pipe thermosensor checks for when the coolant is too hot, and then turns on the aquatuner. With that covered, we can now look at more tools to create more complex automation. These are logic gates, and they're based on real-life components. They modify the incoming signal for different types of control, and we're going to start with the NOT gate. This simply changes the signal from the input to output. So if we summarize this in a small table, when the input is red, the output is green, and vice versa. I've also got here the binary table, and this is actually taken from Wikipedia for the real-life NOT gate. We use this gate where we want the opposite of an output. It's uncommon to only use it with sensors because you can often get the same effect by swapping the sensor itself, for example above and below. But there are some outputs that need to be inverted. Here is a common example from the base game of the space scanner. This outputs green when there is a meteor shower, but at this time we want the doors closed, so the NOT gate changes the signal. Then when there are no meteors, the signal output is red, and then swapped so green is sent to the doors. Note as well that we now have the NOT word to use in our worded logic statement to represent this gate. And from the spaced out DLC, here is the materials study terminal. This outputs green when it's full, but we want to turn on the rad bolt generator when it isn't, so again the NOT gate is used. The next gate type is an OR gate, and this has two inputs and one output. Now we are combining two signals, and the gate will perform logic to work out the output. Let's call these inputs A and B. An OR gate will send green if either A is green or B is green. If both are green, then it will output green too. We can write this out as a table with all four combinations. And again, here is the table for the real-life component. Perhaps obviously, we use these when there are two inputs and we need to react to either one. Here is an example similar to what I showed in the tutorial bite for industrial bricks. The liquid vent to return water to the brick is controlled by two sensors. If the aquatuner is too hot, or there is not enough steam, and the carbon dioxide level is too high, then the liquid vent is opened to return water. This also gives us the OR word to use in the worded logic statement. I wanted to address at this point a wire behavior on overriding signals that I didn't mention at the start. Any green signal on a wire will turn the entire wire green, regardless of all the other outputs onto the wire. I've set up two switches and joined them together, and you may notice that these combinations are exactly the same as an OR gate. If either of these switches are green, the output is green. This means in many situations, especially for two sensors, an OR gate is unnecessary. Where the OR gate is useful is in keeping the inputs separate. Here's a quick example where we have three inputs and we want two outputs, A or B and B or C. If only A is green, then A or B should be green and B or C red. This isn't possible without using the OR gate, as when any of these go green, the whole wire would go green. Next up is the AND gate, which again has two inputs and one output. With inputs A and B, this gate only sends a green output when both A and B are green. You can also see the tables here. For an example use, here is a liquid pump in polluted water from a cool slush vent. In this case, we only want to pump the water when the level is high enough and the temperature is above 0. This would normally be combined with some heating system, which I've not shown. Again, we now have the AND word for our worded logic. The last two types of gate I want to cover in this video are the filter and buffer gates. These are timing gates and are very easy to confuse, but I have found a clear way to remember them. Filter gates delay green signals and hold red signals. Buffer gates do the opposite, so delay red signals and hold green signals. Both have a delay time in seconds that you can choose. To clarify these descriptions, I have both gates connected to a switch. Once I flip this to green, the buffer gate does nothing and lets the green straight through. The filter gate delays this green signal, and I've set these both to 10 seconds. So you can think of it as delaying the green or holding onto the red signal for a time after the input goes green. Now let's flip the switch back to red, and this time the filter gate does nothing. The buffer gate now delays the red signal or holds on to the green. For the worded logic statement, you can think of the filter as being then after an amount of seconds. Buffers are a bit hard to use in this way, and the wording would be something like, if something turns off, then, after some seconds, turn off something else. So an on red statement. There are a few main reasons for using these two gates. Firstly, they can be used to steady a fast-changing sensor. This example is the gas pump at the bottom of a closed base in a triangular funnel. The sensor is detecting carbon dioxide, but it falls quickly in packets and can easily trigger the sensor, which would pump out oxygen. So we can use a filter gate to only pump out if there has been carbon dioxide on the sensor for at least 5 seconds, meaning the gas has stabilized. Next is using them to create a sequence of actions, so one thing happening after the other. This is a common example from a meteor shower setup. The green signal opens the top doors, and we then need time for them to open, then drill the regolith, before opening the lower doors. So a filter gate is used to delay the signal to the lower doors, and here it's set to 100 seconds. Taking this on a step, filter and buffer gates can be used to make purely timing-based circuits. I'm showing here the automation circuit for the door compressor from the tutorial by On Infinite Storage. This only uses filter and buffer gates to time the signals, and the NOT gate resets the cycle. If you want more info on the specifics for this, check out that tutorial by, and I'm including it here to demonstrate what can be done. So I've now covered all of the circuit elements for this first video. The last point here then is combining gates to make more complex systems. Up to now, I've carefully chosen examples with only one gate to keep it simple. But when researching this video, I found that most real game examples were single wire setups and the rest combined gates. I do want to stress again that the sensor, wire, building is by far the most common and powerful bit of automation. So as long as you understood that, then your base will be much better off. Fortunately, I think combining gates is fairly easy, and with the worded logic statement, we can write these out using many of the gate words we have. The only thing to point out is the order of the gates, which will affect the logic. I'm showing here two similar examples, but with the gates swapped around, and their inputs and outputs. The way to deal with this is to carefully use brackets to be very clear which needs to come first. This is exactly the same as with maths operations. Brackets always come first. Here's two quick examples, each with the worded logic statement. First up is another way to do the carbon dioxide base pump, this time turning it on if both sensors detect not oxygen. And secondly, this example is taken from the self-powered oxygen machine build, where the top Atmos sensor controls the hydrogen pump and will also turn on the generator to use excess hydrogen if the gas pressure has been too high for too long. The filter gate output is ORed with a smart battery, so both can turn on the generators when needed. Note that the OR gate is not necessary here, and the cheap OR can be used by simply running the wires together. And that's it for this guide to essential automation in Oxygen Not Included. I hope this helps make your bases smarter, and thanks for watching.